The first window that pops up when we start the Audio Network Analyzer program is this one. It's just a warning window reminding you that the default setup in Windows 7 is not correct for the VAM as we want to use it. We need to make some adjustments, particularly in the Recording tab and the Playback Devices tab of the default audio settings. And we do that like this. Down in the right hand corner of the Windows screen there's a loudspeaker icon. Right click on it and select Recording Devices. Brings up a window that looks like this. Now you have to make sure that the microphone that calls itself 2 USB or 3 USB or 4 or 1, doesn't really matter, that's the one USB audio codec that identifies the VAM board. That should be the green tick default one. And we need to set the properties of that one. So click on it to select it. Properties, levels set to about 3, and the advanced needs to be 2 channels 16-bit 44.1 kHz. That's correct. OK. And then on playback we also want to make sure that the VAM, which on this computer is 2 USB, is selected as the default device. This one I set up earlier, so it's okay. We can proceed to running the main program. We do that by hitting OK. That should bring up the main screen of the program, which looks like this. It's a amplitude plot of dBs against log frequency here, and a theoretical blue line, which at the moment is just 0 dBs, totally flat. The first thing to do is take the calibration readings. Now, if you leave fine resolution unchecked, then it will only take readings at 1 Hz, 10 Hz, 100 Hz, and so on, which is fast, but not terribly accurate. So if you have the time, better to click fine resolution so it takes more readings. And then just hit measure response, making sure that the only thing between the output buffer and the input buffer is a wire. Now it takes a little time to do the measurements at low frequencies because it has to wait for several seconds to get enough of the periods of the waveform to be able to determine the phase accurately. However, once the frequency starts getting up above 10 Hz, it gets quite a lot faster. See it speeding up. Also note that even though this is the calibration run and there's only a single wire between the output and the input buffer, the amplitude is not completely flat that we're measuring. We're seeing slight amounts of gain at very low frequencies. And that's a function of the output and the input stages to the VAM itself. We can see what's happening with the phase by checking the Show Phase button, and we'll see the phase here starts. It's not quite 180 degrees, it's not 0 because of that inverting buffer in the VAM, but it's not quite 180 degrees at these low frequencies either. However, this is a calibration run. We want to use these readings for calibration. So we press this button here, use for calibration. And it now says calibrated at 17 points rather than just not calibrated at all. At this point, we're now all set to try and take an actual reading. Of course, we have to put our circuit in place. So I'll just go and do that. And then we can just simply hit measure response. Again, the low frequency readings will take some time to do because we have to wait for several periods of the waveform, and at 1 Hz and 3 Hz that's several seconds. But as soon as we get up to 10 Hz or so, the readings accelerate. And you can see a response beginning to start. At very low frequencies, we're still looking at about 0 Hz, which is exactly what we would expect from a low-pass filter. it should have no effect at very low frequencies. 0 dBs and 0 degrees of phase shift. As the frequency gets higher and the filter starts to take an effect, the loss of the circuit gets considerable, down to almost 40 dBs, and the phase begins to change and ends up at about minus 90 degrees. Now, this program also gives you some tools to help analyze this. We can add poles into this response. Remember, the blue is a theoretical amplitude response, the green is a theoretical phase response. And if we add a pole by double-clicking here, we'll see what the theoretical response is for a pole at 23 Hz. And clearly it doesn't match the readings very well. But if I pick up that pole and drag it to a higher frequency, then around there, I'm getting a very good match with my experimental readings. The theoretical amplitude goes through the measured amplitude readings almost perfectly, and the same is true down here for the phase. So it looks like this circuit is behaving exactly like it has a 120 Hz pole. That would be our analysis of the circuit then. It has a 120 Hz pole in its frequency response. You can add other poles by double-clicking. If you want to change a pole into a 0, you right-click on it. If you want to get rid of the pole or 0 completely, just drag it off the screen. If you want to put in a 0 at 0 Hz, which is often useful, you can do it by pressing that checkbox there and removing it as so. You can add gain or loss into the entire circuit like this. If you can't get the exact value that you want, then just type it in and press return. By default, it's a typical Bode plot of dBs against the log of frequency, but if you want to use linear frequencies, you can, or amplitude ratios or power ratio rather than the loss in dBs, you can as well, but no idea why you would want to. Standard Bode plot of log of frequency against dBs and log of frequency against phase is pretty much what you're going to want most of the time. A couple of other things to mention. If you can't get a pole exactly where you want it, you can hit that button there and it will bring up this add-on remove poles window where you can type in a value of frequency for a pole and it will add it in here. You can also remove poles and so on, and you can do the same thing with zeros there. But the only other things you need to know, if you wanted to take a single reading at a certain frequency, you could move the slider to that frequency and press single, and it takes a single reading at that frequency. However, these readings will flash, and they're flashing because no calibration reading was taken at those frequencies. It tries to work out a suitable calibration by looking at the nearest points to it, but it's not going to be perfectly accurate, so there is this warning just reminding you of that fact. If you want to remove a reading, just right-click on it, and it's gone. And you can save the results. Just hit save, navigate to a suitable place, and save the text file. Then that you can load into Excel or any other program to further analyze the results, or you could load them back into this program at a later time if you like the analysis tools that this program provides. I think that's just about all you need to know. Have fun.